Because lines are one-dimensional, we consider only length when measuring a line segment. A line segment is measured in linear units such as inches, centimeters, or yards. When a line segment measures 5 centimeters, we write length AB equals 5 cm, or simply length AB equals 5, if the units are apparent or are not stated. The instrument of measure is the ruler. A plane is an infinite two-dimensional surface. A closed or bounded portion of the plane is called a region. When a region, such as R in plane M, see figure 8.1a, is measured, we call this measure the area of the plane region. The unit used to measure area is called a square unit because it is square with each side of length 1. See figure 8.1b. The measure of the area of region R is the number of non-overlapping square units that can be placed adjacent to each other in the region. Square units, not linear units, are used to measure area. Using an exponent, we write square inches as IN squared. The unit represented by figure 8.1b is 1 square inch, or 1 inch squared. In figure 8.2, the regions have measurable areas and are bounded by figures encountered in earlier chapters. A region is bounded if we can distinguish between its interior and its exterior. In calculating area, we measure the interior of the region. We can measure the area of the region within a triangle. See figure 8.2b. However, we cannot actually measure the area of the triangle itself. 3 line segments do not have area. Nonetheless, the area of the region within the triangle is commonly referred to as the area of the triangle. The preceding discussion does not formally define a region or its area. These are accepted as the undefined terms in the following postulate. Postulate 18, area postulate. Corresponding to every bounded region is a unique positive number, A, known as the area of that region. One way to estimate the area of a region is to place it in a grid as shown in figure 8.3. Counting only the number of whole squares inside the region gives an approximation that is less than the actual area. On the other hand, counting squares that are inside or partially inside provides an approximation that is greater than the actual area. A fair estimate of the area of a region is often given by the average of the smaller and larger approximations just as described. If the area of the circle shown in figure 8.3 is between 9 and 21 square units, we might estimate its area to be 9 plus 21 all divided by 2, or 15 square units. To develop another property of area, we consider triangle ABC and triangle DEF, which are congruent, in figure 8.4. One triangle can be placed over the other so that they coincide. How are the areas of the two triangles related? The answer is found in the following postulate. Postulate 19. If two closed plane figures are congruent, then their areas are equal. In figure 8.5, points B and C trisect segment AD. Segment EC is perpendicular to segment AD. Name two triangles with equal areas. Solution. Triangle ECB is congruent to triangle ECD by side angle side. Then, triangle ECB and triangle ECD have equal areas according to postulate 19. Consider figure 8.6. The entire region is bounded by a curve and then subdivided by a line segment into smaller regions R and S. These regions have a common boundary and do not overlap. Because a numerical area can be associated with each region R and S, the area of R union S, read as R union S, and meaning region R joined to region S, is equal to the sum of the areas of R and S. This leads to postulate 20, in which A sub R represents the area of region R, A sub S represents the area of region S, and A sub R union S represents the area of region R union S. Postulate 20, area addition postulate. Let R and S be two enclosed regions that do not overlap. Then, the area of the region R union S equals the area of region R plus the area of region S. Study rectangle MNPQ in Figure 8.8 and note that it has dimensions of 3 centimeters and 4 centimeters. The number of squares, 1 centimeter on a side, in the rectangle is 12. The unit of area is centimeters squared. Multiplication of dimensions is handled like algebraic multiplication. Compare 3x times 4x equals 12x squared and 3 centimeters times 4 centimeters equals 12 centimeters squared. If the units used to measure the dimensions of a region are not the same, then they must be converted into like units in order to calculate the area. For instance, if we need to multiply 2 feet by 6 inches, we can convert 2 feet to equal 2 times 12 inches, which equals 24 inches. So the area equals 2 feet times 6 inches, which equals 24 inches times 6 inches. Area equals 144 inches squared. Alternatively, we could convert from inches to feet. 6 inches equals 6 times 1/12 of a foot, which equals 1/2 foot. So area equals 2 feet times 6 inches, which equals 2 feet times 1/2 foot. Area equals 1 foot squared. Because the area is unique, we know that 1 foot squared equals 144 inches squared. See Figure 8.9. Recall that one side of a rectangle is called its base, and that either side perpendicular to the base is called the altitude of the rectangle. Postulate 21. The area, capital A, of a rectangle whose base has length b and whose altitude has length h is given by capital A equals BH. It is also common to describe the dimensions of a rectangle as its length, L, and its width, W. The area of the rectangle is then written capital A equals LW. Find the area of rectangle ABCD in Figure 8.10 if length AB equals 12 centimeters and length AD equals 7 centimeters. Solution. Because it makes no difference which dimension is chosen as base B and altitude h, we arbitrarily choose length AB to equal B, which equals 12 centimeters, and length AD to equal h, which equals 7 centimeters. Then capital A equals BH is equal to 12 centimeters times 7 centimeters. This equals 84 centimeters squared. If units are not provided for the dimensions of a region, we assume that they are alike. In such a case, we simply give the area as number of square units, or u squared. Theorem 8.1.1. The area, capital A, of a square whose sides are each of length s is given by capital A equals s squared. A rectangle's altitude is one of its sides, but that is not true of a parallelogram. An altitude of a parallelogram is a perpendicular segment from one side to the opposite side, known as the base. A side may have to be extended in order to show this altitude-base relationship in a drawing. In Figure 8.11a, if segment RS is designated as the base, then any of the segments ZR, VX, or YS is an altitude corresponding to that base, or for that matter to base VT. Another look at parallelogram RSTV in Figure 8.11b shows that segment ST or segment VR could just as well have been chosen as the base. Possible choices for the corresponding altitudes in this case include segment VH and segment GS. In the theorem that follows, it is necessary to select a base and an altitude drawn to that base. Theorem 8.1.2. The area, capital A, of a parallelogram with a base of length b and with corresponding altitude of length h is given by capital A equals BH. Given that all dimensions in Figure 8.13 are in inches, find the area of parallelogram MNPQ by using base A, length MN. Solution. Length MN equals length QP, which equals B, which equals 8, and the corresponding altitude is of length QT, which equals h, which equals 5. Then area equals 8 inches times 5 inches. Area equals 40 inches squared. Given that all dimensions in Figure 8.13 are in inches, find the area of parallelogram MNPQ by using base B, length PN. Solution: length PN equals B, which equals 6. So the corresponding altitude length is length MR, which equals H, which equals 6 2/3. Then area equals 6 times 6 2/3 inches squared. This is equal to 6 times 20/3 inches squared. Area equals 40 inches squared. In example 4, the area of parallelogram MNPQ was not changed when a different base and its corresponding altitude were used to calculate its area. Postulate 18, area postulate. Corresponding to every bounded region is a unique positive number, A, known as the area of that region. The formula used to calculate the area of a triangle follows easily from the formula for the area of a parallelogram. In the formula, any side of the triangle can be chosen as its base. However, we must use the length of the corresponding altitude for that base. Theorem 8.1.3. The area A of a triangle whose base has length B and whose corresponding altitude has length h is given by A equals 1/2 BH. In the figure, find the area of triangle ABC if length AB equals 10 centimeters and length CD equals 7 centimeters. Solution: with segment AB as base, B equals 10 centimeters. The corresponding altitude for base segment AB is segment CD, so h equals 7 centimeters. Then area equals 1/2 BH becomes area equals 1/2 times 10 centimeters times 7 centimeters. Area equals 35 centimeters squared. Corollary 8.1.4. The area of a right triangle with legs of length A and B is given by A equals 1/2 AB. Corollary 8.1.4. The area of a right triangle with legs of length A and B is given by A equals 1/2 AB. Corollary 8.1.4. The area of a right triangle with legs of length A and B is given by A equals 1/2 AB.